There is a fundamental connection between focusing and imaging. That is, in any area of physics that we need to create a well-resolved image of an object, we've got to have a reliable means for focusing waves. One useful concept for assessing the resolving power of an imaging device is the point spread function. The point spread function is the impulse response of an imaging device. For example, if we use a concave mirror for imaging, then the point spread function is the image we get from a point source. The more impulsive and the more compact the point spread function is, the higher is the resolving power of the imaging device. Here I'll give you an example of a rather more complicated imaging apparatus. When Hubble telescope was launched into its orbit in the beginning of 1990s, the scientists at NASA quickly understood that there was something seriously wrong with the main mirror of the telescope. And this was because the images that the telescope sent back to the Earth were not as focused and as resolved as they expected them to be. Here on the left, you see an image of a single strong star, which is basically the point spread function of the telescope. And this impulse response, as you see, is spread out and defocused. And because of that, the image that we get from the spiral galaxy is also defocused and blurry. Now, in this case, they knew what the exact problem was, and they could design a fix. And after they applied the fix, here are the same two images after the correction was applied. We see that the impulse response is now much more focused. And because of that, the image of the spiral galaxy is also of a lot higher resolution. Now, today I'm going to talk about a similar problem, but in acoustics and in this geophysical setting. An important problem is in geophysics is to understand the seismic source. And we would ideally like to be able to image the source. And this could be an earthquake source or a micro-earthquake source. In this case, our imaging device is a bunch of receivers which samples the wave field generated by the source as data. And we would like to somehow be able to backpropagate these samples data into the medium to create a source image. And to do this, we often exploit the time reversal invariance of the wave operator through techniques which we call the time reversal focusing. Now, time reversal focusing is a simple process with 3 steps, which I'm going to illustrate to you with a numerical example. Suppose we have a medium with known properties. This is an acoustic medium. And that somewhere inside this medium we have a point source, which is surrounded by receivers represented by the white diamonds. Now, this source will generate energy, and I'm going to switch to the wave field at the time of source activation. The energy of the source will propagate throughout the medium, and it will eventually be sampled by the receivers as time signals. In the second step, we time reverse these time signals, and we inject them back into the medium. A new wave field will be created, and it will converge and propagate backwards towards the source location, and we could scan this wave field and stop where the source is focused. Now, this is an ideal image. But the problem is that when the acquisition geometry is incomplete, the ability of the time reversal process to create such a sharp focus will be compromised. To see that, I'm going to repeat this experiment for you with just 8 receivers on top right. And if I do that, here is the focus that we get. I'm going to zoom into this white square and blow up the image so that we can see that the impulse response or the point spread function is now distorted, as you can see, and is elongated in a certain direction. And to try to image more complicated sources with an imaging device with this point spread function will lead to blurry and defocused images. So we have a problem, and we need to find a solution so that with these 8 receivers, we get a better and more impulsive point spread function. And this brings me to the solution that we provide to this problem as the Backus and Gilbert focusing. Now to start to see how this method works, let us assume that we have an acoustic medium with known properties. Now in this medium, we have n receivers, and these receivers start recording at time 0 and they all stop recording at time capital T. Now suppose that at some time, unknown time tau, and at some unknown location C, an impulsive point source happens. So we can represent the source function as the product of two delta functions. So this source generates energy, and the receivers will record this energy as data. So D sub I represents the data recorded by receiver at station number I. And in this case, the data is the green function associated with the source. What we would like to find are the optimized signals that I represent by AI of t, that upon injection will create a new wave field phi, which will backpropagate and collapse into the correct source function. And this injected wave field phi can be represented as the sum of the convolution of the injected signals, AI of t, with the green functions associated with each receiver. Now to achieve the goal, that is to achieve the wave field phi that will collapse to the correct impulsive source, we define an objective function with this form, where we minimize the difference between phi, the injected wave field, and the time reverse source function. And we are doing this summation over all time elements and over the spatial elements within an optimization window W, where W is a limited area that contains the source. Now, we don't know the exact location of the source. However, we often have a good estimate of the source location. And this estimate is enough for us to define this limited area. The size of the optimization window should ideally be 2 to 3 times of the dominant wavelengths in the experiment. Going back to the objective function, we can substitute phi with its definition, the convolution of the optimal signals with the green functions. And then we can transform this objective function from the time domain to the frequency domain, so that we get a separate objective function for each frequency component separately. And this objective function is what we should minimize with respect to the unknown coefficients AI of omega for each frequency independently. If we do this, we end up with a system of linear equations, which I compactly expressed as the one shown here. Here, gamma on the left is an n by n matrix with its element ij defined as the expression shown below here, where we are summing over the product of the green functions associated with receivers at I and j, and the summation is carried out over within this optimization window W. The thing to know is that if we know the velocity of the medium, we could compute the green functions for the receivers, and therefore we could compute gamma. So gamma on the left is known. D on the right-hand side is an n by 1 vector, which is defined as the expression shown here. And even though this expression contains the unknown source parameters, tau and c, time and location, we don't need to know these parameters explicitly, because what this expression shows is indeed the frequency components of the data that we would record in the field. So as long as we have the data, all the information that we require to know about the source is encoded within the data, and therefore the right-hand side of the system of equations is also known. What is left is the n by 1 vector A, which is the unknown vector, and we should solve this equation separately for each frequency to find the coefficients AI of omega. And finally, in the last step, we do an inverse Fourier transform to take the time signals, the optimized time signal that we should inject. So we inject these time signals, and we get an optimized wave field phi, and all we need to do is to scan this optimized injected wave field phi within the optimization window W to get the source image and to find the source location. Now, I've done this experiment for you for the simple numerical test or example I showed you before. And I'm going to show you the signals associated with 4 receivers. Receivers number 1, 3, 5, and 7. And I'm going to compare them with the data. Here on the left column, we see the time reverse data recorded by these receivers. The strong event is the direct arrival energy, and the weak event is the reflection energy. On the right, we see the Backus and Gilbert computed trace associated with the same receivers. And note that how these signals are different from the data signals in both amplitude and shape. In particular, I draw your attention to how the reflected energy in the Backus and Gilbert trace is amplified compared to that same energy, reflected energy in the data. And we will see the significance of this amplification shortly. But before that, I would like to go back to the source image that was produced with time reversal, as we saw earlier. So this is the time reversal image. And finally, I can show you the Backus and Gilbert image. So time reversal, Backus and Gilbert. Once more, time reversal, Backus and Gilbert. So we have managed to improve the point spread function of our 8 receivers. Now the image that you see here is confined within the optimization window W. If I zoom out, you see that outside W we have energy. And in particular, I would like you to pay attention to the strong burst of energy indicated by the white arrow. This is the energy that is created by the amplified reflections I showed you earlier. This energy travels before the main arrival energy. It gets reflected off the reflector at 500 meters, and it illuminates the target from underneath. That means with Backus and Gilbert focusing, we are effectively using the discontinuities in the acoustic medium as an acoustic mirror to augment the incomplete acquisition. Now, I have basically told you the gist of my story and how the method works. But before finishing the talk, I would like to mention a couple of more points. The first thing that I want to talk about is the connection between this method, the Backus and Gilbert, and the time reversal. Because even though they might look very different, there is actually a very nice connection between them, as the time reversal is a special case of the more general Backus and Gilbert method. To see this connection, let's revisit the system of equations we saw earlier. Gamma is in general a dense matrix whose elements will determine the way different receivers must work with each other to achieve the best focus. Now, if I crudely approximate gamma with an identity matrix, then what I get is this new system of equation. Now remember that we solved this system of equation in the frequency domain. And in the frequency domain, the complex conjugation that you see on the right-hand side corresponds to the time reversal in the time domain. That is, if I do an inverse Fourier transform, I get an equation which exactly describes the same process as time reversal in the time domain. This means that the time reversal is just a special case of the more general Backus and Gilbert method. The second point that I want to talk about is the issue of imaging distributed sources. In the derivation I showed to you today, I assumed that we have our sources an impulsive point source. But this was just for simplicity. In fact, in the paper and in Appendix A, I show that the theory is general and it works for any complicated source. But intuitively, a complicated source in space and time could be thought of as a collection of impulsive point sources in time and space. And we are dealing with a linear process, therefore the whole thing stays valid even though we have a complicated source. And to illustrate this, I'm going to go back to the example again, but this time I'm going to repeat the process for a source which is now comprised of two point sources with opposite polarity. This is kind of a dipole source with the radiation pattern. So if I try to image this source once with time reversal and once with Backus and Gilbert method, this is what I get. On the left, you see the true dipole, which is horizontal in this case. In the middle, we see the time reversal image of this source. And on the right, we see the Backus and Gilbert image. We see that Backus and Gilbert has produced a more focused and compact image. And also, it has done a better job in delineating the horizontal orientation of the dipole. And this stays valid even if I rotate the dipole orientation, because we have a radiation pattern, and if I rotate the dipole, the receivers will see different types of energy. So I'm going to rotate this to 45 degrees, 90 degrees, and 135 degrees. And do this one more time. Horizontal, 45 degrees, 90 degrees, and 135 degrees. In each case, the Backus and Gilbert image has outperformed time reversal in delineating the orientation of the dipole. To summarize the talk, we approach wave focusing as an optimization problem with the goal of mitigating the adverse effect of incomplete acquisition on the time reversal process. We formulated and solved the problem in the frequency domain. However, as we show in the paper in Appendix B, it's also possible to solve this problem in the time domain. And in that case, we end up with an iterative method, which in many senses resembles the least squares migration. In applying this method, we have made three main assumptions. The first assumption was knowledge of the medium. We need this information to compute the green functions for each receiver. The second assumption was an estimate of the source location that we used to define the limits of the optimization window. And the final assumption, the third assumption, was that we assumed that the medium is acoustic. Now, if we want to use this method in real earthquake or microseismic applications, we've got to generalize this method for application in elastic media, and that's because the Earth is an elastic medium. And this generalization of the method for application in elastic media will be the main subject of my talk tomorrow. Thank you very much for listening.